Hi. Let's continue nonlinear models. The first is what is called logistic growth. So it is about the population growth. So if you have some population, say people or microbes or viruses and so on, put in some substrate which permits them to grow. Then in the simplest model, which we considered already, linear model, the rate of growth is proportional to the actual number, existing number of these individuals. Yeah? So the growth is exponential, and the exponent is such a function which grows very fast, faster than any polynomial, for example. And so very soon the population exceeds any reasonable size. For example, if you let the people proliferate with the same constant rate, then after some relatively small time, it is about 1,000 years, maybe 2,000, the total mass of population will exceed the mass of the Earth, which is hardly possible. And so we have to introduce some limits of growth. So the population grows, but it cannot exceed some limit, which depends on the situation. No, for example, if you put a colony of bacteria in the petri dish and it starts growing, so its size cannot exceed the size of the dish by definition. So we have this limit that cannot go further. And next hypothesis is that the growth rate first is proportional when the number of individuals in this population is small, then its growth is not restricted. And so the natural growth rate without any obstacles is constant. I mean, the linear growth. dn dt equals k times n. It is the linear growth. So the growth is proportional. Now it is natural to assume that when the density or the number of individuals is small, then it is still described by this equation, since there is no obstacles. No, if there really is no obstacles. No, such things happen, but not very frequently. For example, when the rabbits were first brought to Australia, and soon they proliferated to the whole continent, then for the first few years their growth was exponential. And then they reached their limiting density such that they could not proliferate further because there was not enough food for them, and existed at this level. So the better equation is dn dt equals some function f of n. Yes, and so here, what is f of n? If it is t, it is this n. Then the first step for a small number of individuals, it is more or less exponential growth, and then it becomes less fast, and then it goes to some limit, which is, say, the natural bearing capacity of this surrounding, of this place. Say the size of Petri dish, or the size of Australia, the amount of food in this landscape or in the ocean, and so on. So this is the qualitatively the typical picture of evolution of the number of individuals in this say colony or no population. It is the biological systems are very complicated, so they include so many parameters that sometimes even this picture does not reflect what happens. For example, we can see sometimes if you take, say, a colony of mice in a big, relatively big space, no, like the size of this room, and they have enough food and enough place with here. They first proliferate exponentially, then more or less stabilize, and then after a few generations it goes down, and all the colony gets extinct. The number of the mice becomes zero. Yeah, and it is this effect cannot be described by such equation, so it is requires much more involved mathematical model, and this problem I think is still not solved. So we consider the simplest situation with this function f of n. So first of all, this function for small n should be more or less linear. No, it's enough that it is differentiable. And then there is some limit n, so that at this, if point I am defined it by b, denoted by b, this function becomes again 0. So we have this function f of n. No, we can even think that for larger n it becomes negative. So here we have the, say, the slope at the 0, no, some a, yes, a is not angle but the slope, like this. And then we can consider example of such function f of n equals a n times, so I want to consider to find a quadratic function such that it has a slope a here, and it is 0 at 0 and at the point B. 1 minus n over b. Yeah. So this function, if you differentiate it at the point 0, its derivative is n. Is a, and f of b equals 0. If you substitute b, n equals b, it becomes 0. So this is no typical example of such a function, and we will study an equation with this function. So our equation is the following. Let me little change notation. Just make an abstract. Dx dt equals this function. Ax 1 minus x divided by b. No, it is nothing unusual in this equation, so let us solve it. It is autonomous equation, so we can first draw the phase picture of this. So it is the point 0, it is the point B. For x between 0 and b, this function is positive. This is positive and this is positive. And so the motion is in this direction. The, x as a function on t is growing here, so moving in the direction from 0 to b. If x is more than b, then this factor is negative. So here it is moving in the direction of b from the above. No, at last it makes no sense as a population problem, but formally we can consider even negative x. Then this is negative, this is positive, and so here we have this picture. So we have two fixed points, 0 and b. 0 is unstable fixed point, b is stable fixed point, and so the evolution goes in this direction, and then we approach point b, and our motion evolution becomes slower and slower, and at last we will have a solution will go tend to b when t goes to infinity. Now, let us now solve this equation and see how it looks. So, dx divided by ax 1 minus x over b equals dt. Yeah? Integral dx ax 1 minus x over b equals integral dt equals t minus t0. Or t plus. Okay, let's t plus t0. Now we have to find this integral. Let us do it. Integral dx ax 1 minus x over b equals, let me multiply it by b divided by a. It is b over a integral dx divided by x b minus x. Okay? And now I decompose it into elementary fractions. So 1 over x b minus x equals, say, alpha divided by x plus beta b minus x, which is equal alpha b minus x plus beta x divided by x b minus x equals alpha beta plus minus alpha plus beta x divided by x b minus x which is equal to, yes, and this is equal to 1. So we have alpha beta equals 1, alpha equal beta. Alpha b. Alpha b equal 1. So alpha equals 1 over b equals beta. And so our integral is integral, b divided by a integral 1 over b x plus 1 over b minus x. One over b here and here. 1 over b dx. Now it is 1 over a here integral 1 over x logarithm x integral 1 over b minus x. No, here x less than b. Yes, we are between a and b. So it is minus logarithm b minus x. Yes? Equals 1 over a logarithm of x b minus x. And so t minus t0, yes? And so we write 1 over a logarithm of x b minus x equals t minus t0. t0 depends on initial condition. Logarithm x b minus x equals E AT times E minus AT0. Now x over b minus x. So x equals b minus x times E AT minus AT0. So x 1 minus E AT minus AT0 x here plus equals B E AT minus AT0. Now let us, yes, here is bracket. X equals B here E AT minus AT0 divided by 1 plus A 1 plus E AT minus AT0. No, let us divide by this. Let us divide by this exponent. It's more convenient. It is b divided by 1 plus E minus A, T minus T0. So here T0 is a constant, and this constant depends on initial condition. So let us solve the initial value problem. X of 0 equals x0. So let us substitute x of 0 equals b 1 plus e minus at for t equals 0, so minus a times minus t0 at0 equals x0. Now we have to find at0, or better e to the power at0. B equals x0 plus x0 e at0. So b minus x0 equals x0 e at0. Divide by x0, b x0 minus 1 equals e AT0. No, you know what? In the answer, in the solution, we have not T0 itself, but it enters in the form E minus AT0. Yeah. So this means that you can write this solution like this. This solution x of t equals b divided by 1 plus e minus t times e a T0. Minus AT. EAT0. EAT0, we know what it is. It is B divided by 1 minus B at 0 minus 1 E minus AT. Yeah, so this is solution. And now let us look what we have. F0 is between X0 and B. Yes? So this means that B over X0 is positive and more than 1. So this is positive. Now, for t equal 0, it is one moment. 1 plus, I'm sorry, plus. So this is positive. Here is 1. Now A is positive. For t equal 0, it is 1. It is 1 plus b of x0 minus 1. B divided b, it gives exactly x0. So it satisfies the initial condition. And when t grows, this becomes this goes to 0, this is constant, positive constant, this exponent goes to 0, so this term goes to 0, and the limit is b over 1, it is b. And this constant, so this decreasing, so the denominator is decreasing when t grows, and so all the fraction is increasing and goes to the limit 0. So the solution its graph of solution is the following. So this is B. We started at the point x0, and then it increases and goes like this. Now, if you wonder what happened before, for example, we started observing our system at some moment, but possibly something happened with the system before. We have just to substitute here negative t. If t is negative, then this is growing exponential when t goes to minus infinity. There is positive number, so the denominator goes to infinity, numerator is constant, so the fraction goes to 0. So it looks like this. So we have this graph, this curve. It has here some inflection point. Yes, so it is second derivative here is positive. Here it is negative, and we have inflection point where the second derivative is 0, and so this is the curve which is called logistic curve, and by some reason I don't know why this name. So we have solution, we can do whatever we want. Now for example, consider the following problem. I don't think that it is very realistic, but just example. One moment, let me find it. Yeah, here it is. So the problem is the following. You have a pond, a small lake, and you know that if we don't clean it, its surface is becomes covered by a plant called duckweed. It is small leaves, size of penny, which are floating on the surface, and very soon they multiply in numbers, and soon they cover all the surface of the pond. Therefore, the pond should be regularly cleaned. And we can assume that this species of plants is growing, and the part of the surface of the pond, x of t, it is percentage of the surface covered by this plant. And so this part is between 0 and 1. Yes. First of all. So in this case, this quantity x cannot exceed 1. So, and we assume, let us describe the development of this weed by logistic equation. It is not maybe not very accurate description, but it is a little, maybe a little more accurate than purely exponential growth description by linear law. So this means that equation is dx dt equals ax 1 minus x, because b equals 1. Yeah. So again, x is the part the area covered by the width, like this. Here it is covered by the width, divided by the total area of the pond. A is unknown, and we have the following. So at the beginning of our observations, x of 0, x0 is say 0, 0, 1. Just 1% of the surface is covered by the dark width. Now the unit of time here, no, it is natural to take as the unit time of time a week. So after 1 week, x of 1 equal 0, 0, 5. So after 1 week, we observe that already 5% of the area of the pond is covered by the dark weed. And the question is what will happen after 1 month? So after 1 month is 4 weeks approximately. So after 4 weeks, how what is which part of the pond will be covered by this weed? No, to this end we have to find A in this equation, and we have a ready solution. We have only to substitute here x0 and x of 1. So x of t equals b, b is 1, divided 1 plus b over x0, x0 is 0.01. It is 1 over 0.01, it is 100. Okay, 1, 0, 0, 1 minus 1 e minus at equals 1 divide 1 plus it is 100 minus 1, 99 e minus at. Now we have to find a, or maybe it's better to find or first e minus at. So x of 1 divided by 1 plus 99 e minus a, because t is 1. Yeah. No, I make life easier for myself. And this is equal to 0.05. So this means if you take inverse, 1 plus 99 e minus a equals 1 over 0.05 is 20. Uh, 99 e minus a equals 19. E minus a equals 19 over 99. You know what? We can find, okay, we can find this A but better to see that x of 4, which we have to find, it is 1 plus 99 e minus a minus 4a equals 1 divided by 1 plus 99 e minus a to the power 4. And we know what is e minus a. It is 19 over 99 equals 1 divide 1 plus 99 times 19 divided by 99 to the power 4. No, it is simple arithmetics. Where is my... Oh, no, okay, let me write down the answer because I cannot find my arithmetic. It says 0.88. So, initially only 1% of the pond was covered by the wheat. After 1 week it was 5%, and after 4 weeks from the beginning, after 1 month, 88%. If you assume that the growth is exponential, then after a month the result would be more than 1. So it is more than the total area of the pond, which is impossible. So you see that this equation now takes care of this the natural bound of the growth. Yeah, so it is again, it is a very coarse model of what can happen, and we cannot even say that it is close to something, but sometimes it works. In fact, there exist many different models of the population growth, and they are calibrated on the true statistical data, say for the human growth or for some natural growth, yes, or in medicine we can talk about the tumor growth in people with cancers. So it is not, in fact, in all these cases, the underlying nature is much more sophisticated than in simple physical or chemical or chemical or engineering systems. Yeah, and so the description by such primitive equations cannot be accurate. So it is pure empirics. But if you take into account more parameters, more mechanisms, first we have to find these mechanisms, then our prediction may become more accurate. So this is what the ecologists are concerned. They are building such more advanced models which describes the things more accurately. But what I can say, simple linear model of growth catches some feature of this growth. First it is growth, and it can estimate the rate of this growth how it will grow, at least in some circumstances, say for very sparse populations without any natural enemies and so on. But it cannot give you predictions for a long time. It fails there. So this model can be a little better because it takes into account one more factor, that there exists some limit, some factor which limits growth. So when the population approaches to this boundary, upper boundary, it stops growing. Yeah. So it is one more factor. Other models take into account more factors, and so they produce, for example, the oscillating population. Yes, how it happens in nature. It is the famous Lotka, Voltaire and further models. I don't think that we will study them. So we can catch some interesting phenomena and even predict them. But our prediction would be mostly qualitative. Okay, it's too much about these difficult problems. So let us go to some other system.